Now we have seen all the concepts in the functional paradigm that we will use in this course. So we can define its full kernel language. We will use this kernel language to understand exactly what a functional program does, how it executes. No hand waving, nothing hidden. You will understand everything. We have already used it to see why list functions are tail recursive. Remember, you can create a list pair with an unbound variable before doing the recursive call, which will then bind the unbound variable. So this is a consequence of single assignment. But we'll also use the kernel language as part of the formal semantics. It's one of the two main parts of the formal semantics, the other part being the abstract machine. And each time we introduce a new paradigm in the course, we will define its kernel language. And each of these kernel languages will extend the one we see right now, the functional kernel language, with a new concept. Usually we will add just one concept to go to another paradigm. So the paradigm will superficially seem very similar, and in fact we'll be able to exchange data and use both paradigms in the same program. But the new concept will introduce many different ways of thinking, so that the new paradigm will also be very different. So this is what we have seen so far in the functional kernel language with a number of statements. So the skip, sequential statement here, the local, the binding, the if, the procedure, declaration, and call, the case, and the number of values, numbers, and lists. So there are things here that are missing. Here there are values. Basically, values are missing here. So to become the full kernel language, this partial kernel language needs two changes, which we have seen in today's lesson. So it needs, first of all, procedure values, and second of all, record types. Here, in this partial kernel language, the procedure declaration is a statement, so we don't really see what the procedure is. Actually, we have to replace this so the procedure declaration becomes a value. And this we have already shown how to do it with procedure values. So the way we do it is, well, we will remove the statement here. We will add a new value called procedure, and this value will be an anonymous procedure, which when it's created will create a procedure value in memory. So we have then as values numbers, procedures, and lists. So that's the first step. The second step is the compound data types, the records. So far we have only seen lists. Well, we generalize that. So we remove the list type and we add a record type here. Records which subsume lists. So a record is either a literal, which is a kind of atom, or a literal followed by a set of fields and field names and field values, field names and field values. The field values can be any variables. So this is the record. And with this, we have the complete kernel language. So this here, these are all the statements, and these are all the values in the complete kernel language of the functional paradigm we will see in this course. So we will define the semantics for this kernel language, and we will define all our constructions, such as data abstractions for object-oriented programming, using this kernel language. So this slide then shows the kernel language of the functional paradigm as we will see it. And every instruction here has a reason for being here. For example, let me just attract your attention to the skip instruction, which does nothing. Why is this instruction important? Well, because it allows other instructions to be simplified. For example, in the if we don't want to use an else, we can put a skip. Or in the case also, we can use a skip. So every instruction here has a reason for being there that's important. So to finish today's lesson, let me take a step back and explain how our approach, which is the kernel language approach, situates itself with respect to other approaches to understand and to define the execution of programming languages. So we start here with a practical programming language. In fact, there are three main approaches for understanding programming language. There is the kernel language approach, the foundational calculus approach, and the virtual machine approach. And let me explain these three different approaches. So let me start with the foundational calculus. The foundational calculus is useful for the mathematical study of programming. What you do is you reduce the languages to really the minimum set of elements. If you look at, for example, the lambda calculus or the pi calculus, you really have a very, very small set of concepts, which means that if you want to do real programming, you have to do lots of encoding. Also, it's not a very efficient way programming, but it lets you prove theorems about the expressiveness of your concepts and compare different languages. So it's really the strongest way to understand languages from a mathematical point of view. So that's the foundational calculus. Another approach is called the virtual machine approach. The goal here is efficient execution on a real machine. So a virtual machine has incorporated concepts that correspond to processor architectural concepts that you need to make the execution efficient. And for example, probably the most well-known virtual machine is the Java virtual machine, which is used for the execution of the Java language. It's also used, for example, by compiler designers who target the virtual machine for compiling a language efficiently into efficient machine code. So those are the two approaches that exist. The third approach is the kernel language approach. And here the goal is not mathematical study per se or efficient execution per se. The goal is to help the programmer, the human programmer, in reasoning and understanding his programs. So all the kernel languages in this course are examples. The concepts are chosen so that programmers can express what they want to do. It's not a minimal set of concepts like in a mathematical study. It's not a set of concepts that are targeted toward processor architectures. No, they are chosen for the programmer so that the programmer can understand programming techniques. They do have implementations, of course, and technically they can be considered as foundational calculi. A kernel language is a kind of process calculus, but the goal is quite different from the process calculi used in mathematical study. Here, the goal is to help the programmer. So you've already seen how we do this. We can express many techniques, many paradigms in a very compact and understandable way. And with precision, we can define them rigorously. This really is the kernel language approach.